Okay, good morning. So today's lesson is actually a very important lesson. In geometry, there are three theorems. Of course, there are essentially two theorems. They are more or less the same thing. Top triangle, transversal, and bisector theorems. Okay, so let us try to understand the content and some examples regarding this. If you have a triangle ABC, I'm trying to describe you what is the top triangle theorem. Yes. So if I have a triangle, let me call it ABC. And then if I draw a transversal line parallel to one of these sides, it doesn't matter which one. Of course, the word top here, I will tell you why they call it top, but it doesn't matter if it is top or on the right or on the left, it doesn't matter. So if you have a triangle and then you draw a line parallel to one of these sides, no matter which side is that. But let us consider I draw a line parallel to this side so that it intersects these two sides, not from here. I want to draw it in a way that it intersects these two. Okay, so for example, let me just draw this. And then let us say this point is M, this point is N. The reason they call it top triangle theorem is because it makes a triangle on top of this line. But it doesn't matter, I can draw this line like this, parallel to that one, then I will make a triangle on the right side, or I can draw a line parallel to this side, and I make a triangle on the left side. But commonly, this is a new word for me, it's probably in Swedish books, it's called top triangle theorem, but it's a little bit of misnomer. Okay, so what is the content of the theorem? It tells you that if you do that, you construct a triangle which is similar to the original triangle. That's it. Okay, so if I draw a line parallel to any side, I make a new smaller triangle. Might be a smaller is a better name than top. The problem is that this triangle that I construct in that way is always similar to the original triangle. Yes? So do you remember what was the main theorem in Math 1C regarding similarity? Yes? No, that is a little bit different concept. We haven't studied that yet, yes. Yeah, angle-angle theorem was the main theorem. If two angles from one triangle are equal to two angles of another triangle, then the two triangles are similar. Okay, so here the claim of this theorem is to say that triangle AMN, which is called the top triangle, and the original triangle ABC are similar. This is the symbol that we used for similarity, if you remember. That's the claim. Okay, so every theorem is a claim that we have to prove it. Sometimes we can prove it because it is the right level of knowledge of your math. Sometimes we cannot prove it, we have to accept it, and if you're interested, you have to study them on your own in more advanced topics. But this is one of those cases that we immediately understand the reason if we remember what we learned in Math 1C. So why do you think this triangle that I generated in this way is similar to the original triangle? Exactly as Ismail said, we want to use angle-angle theorem. So you need to convince me that two angles of this triangle have the same sizes of two angles of this triangle. One of them is very clear, isn't it? Yes. Angle A is not only an angle of the smaller triangle, but also an angle of the bigger triangle. So I would say that angle A equals angle A, the angle in common. There is one more angle that you need to convince myself. For example, let us concentrate on this angle M and this angle. You can have a feeling probably this angle M is equal to this angle B, but why is that?
Because those two lines are parallel and the AB is transversal.
Transversal. So do you remember I told you a Z shape or any other way? So this angle and that angle are always the same. So if you consider this Z shape, you understand that, let me call these angles, let me call this U, this V, this W, for example. So do you see this Z letter here? This is a real Z because these two lines are parallel. So two lines are parallel, another line is transversal, so it is guaranteed that V and W are the same, and of course V and U are also the same. So U and W are the same. But let me remind you, if you have two parallel lines and a transversal line, we have 4 acute angles and 4 obtuse angles. Obtuse angles are all equal, acute angles are all equal. That was the content of that theory. So based on that, it is done. So we say that MN is parallel to BC because I drew it in that way myself, and I would say that AB is transversal and AB is transversal. So what can I conclude from these two? These 3 dots usually in math books means we can conclude from these two. If there is no space to go forward, you just go vertically by doing this. Okay, so what does it mean? It means that, sorry, this is not correct, because this is just the conclusion from here. Anyway, I have to open a space here. So from this one and that one, I can conclude that angle U and angle W are equal. Now I would say that angle A is equal to angle A, angle U is equal to angle W. So by angle theorem, do you remember we summarized it as AA, angle theorem? This means that the triangle AMN is similar to triangle AB. Yes? No, but this is the proof of the theorem. Mainly, you need to use it in problems. But anyway, I don't want to get confused of this bad name, top triangle. You can draw this in any other way. So for example, if I have this, I can decide to draw a line parallel to that one, yes? And then what happens, there is no top triangle, there is a right triangle here. So this smaller triangle will be similar to the original. And if I drew it the other way around, that smaller triangle is again similar to the previous. So mainly, this is it. So I don't know why they have separated these theorems. A little bit confusing for me as well. Anyway, so transversal. So what is the transversal theorem, which is important one? And that is not something new, you know. When we know that two triangles are similar, what can I write? I can write the ratio of the corresponding sides are all equal. Yes? So, for example, this top triangle or the smaller triangle has 3 sides. One of them is AM, one of them is what? AN, and the other one is MN. So you know that if two triangles are similar, that the ratio of corresponding sides are also equal, are all equal, yes? So do you remember? So there are two equalities that I can write here. So if I write AM, so AM to what should I write here? AB, and then AN, AC, and then finally MN to BC. Yes? So this is what I want you to know, okay? So if you draw this line parallel, so let me just put a line here. So this line is parallel to this line. Then what can you write? You can write AM to AB is equal to AN to AC and is equal to MN, yes, to BC. So this picture you have to have in mind. That is the content of transversal theorem. But the book has used this transversal theorem for a different setup that I want to discuss about that to you as well. Is that understandable? Okay, so be careful. When you write AM, you have to write AB. And when you write AN, you have to write AC below it. And then you are allowed to write MN over BC. So that is something that you know. But what they have written for this in the book is this. What they call transversal theorem is that if you have this setup, And by the way, let me not to draw this more than that is necessary. So here is M. So here, this line is parallel to that line. Let me consider this side X and this part A, and then this part Y, and this part B. This A is this small part, not the whole thing. A very nice relation holds, you know, so you can write X over A is equal to Y over. Okay, so this is something they consider transversal theorem. So if you have a triangle and a line is drawn parallel to one of the sides, for example, this side, then you have four small pieces on the original triangle. If you call this length x, this small part A, and this length y, this is small part B, you can always write x over A is equal to y over B. But if you want, you can write x over y is equal to A over B. That's also possible. So you have to decide what you want to do, because I hope that you understand that is exactly the same thing. Yes, because if I say x over A is y over B, it means x times B is equal to y times A. That's also the same thing. X times B is equal to y times A. It depends which one you prefer. I myself prefer to write it in that way. X over y, x over A is y over B. But why this is true? This is not exactly what we have here. Okay? So why this is true? We need to understand that one. And be careful. If you use this, how many fractions you can write? You can write 3 fractions. If you write this part to the whole part, then you can write this part to the whole part, and then you are allowed to write this by that as well. But if you decide to write x, which is one part over another smaller part, you can write the other one, but you lose to write the third one. So that's the only thing that you have to be careful about. Okay? So let me not confuse you. First of all, tell me, why do you believe that this number divided by that number in this picture should be exactly equal to this number divided by that number? I want you to see that that is not exactly what we have here. Yes? Because x is the side of this smaller triangle, but A is not a side of any triangle. It's just a line segment. Yes? In this case, AM, AN, MN are sides of the smaller one, and AB, AC, and BC are the sides of the bigger one. Yes? Here, X and Y are sides of the smaller one, but A and B are not sides of any triangle. They are just line segments. Why this is true first? Why do you think this should be true?
That this theorem is true.
Yeah, that's a theorem. You want to prove the theorem first, so that validate to use it. Yes.
I wrote like x divided by x plus a
Uh-huh.
is equal to y divided by y plus b.
Yes, that's correct. And then we have to continue a little bit algebra to come up with this expression. That's correct. So according to this theorem, what can I write? I can write x over what? X over the whole thing. The whole thing is not a, it's a plus a, x plus a. Is equal to what? Y over y plus b. In this case, I can write z and w. If you want, I can continue to write z and w, but this is not necessary. So I don't write it. Yes? So this I can write. Agree? This is exactly this theorem, yes? I can write, because this one is parallel to this one, I can write this to the whole length is equal to this to the whole length. If I want, I can continue and write this to this. In this problem, because my goal is to prove this, I don't bother to write this even though it is correct. I don't need it. But I want you to understand, you have to write x over this expression, or over this length, but this length is not a, this length is x plus a. And the same story here, y over y plus b. Is that understandable? So I am using that fact in this new picture and I conclude this. But this is not what I want to show. I want to convince myself that I can go from here and show that this one is also true. What can I do for it? Yes. So I would say that, okay, this fraction is equal to this fraction. So what can I conclude? I can conclude that x times the whole expression is equal to this times that expression, yes? But then let me multiply things, so it becomes xy plus xb. This is algebra, this is not geometry anymore. And then this becomes yx plus ya. But now suddenly you see what happens. Xy and yx are the same. So if I move one of them to the other side, the sign becomes negative and they cancel out. And then what is left for me is xb is equal to ya. Yes? And now I divide everything by AB. If this one is equal to this one divided by AB should also be equal to this one divided by AB. But now what happens? This B and that B are simplified, so I get x over A, and here this A and that A are simplified, I get y over B, and that is what I want to prove. Okay, so I want you to understand which one you are using. This is not similarity. This is a consequence of similarity. Yes, similarity gives me this relation. Okay, but sometimes this is useful. For example, if I give you these three numbers and I want you to find the last one, it is very easy to use this. For example, if I give you this is 3 centimeters, this is 5, this is 3, I don't know. Let us say this is 6, and I want you to find B. For example, this is an E-level question. They give you a picture like that. They give you these three numbers, and they ask you find the other number which is not known. Okay? So of course you can use that if you like it, but here in this picture, this new setup is simpler to use. So if you want to do that, you would say that according to transversal theorem, I am allowed to write 5 over 3 is equal to 6 over b. And then I say 5b is 18, and I'm looking for b, so it becomes 18 over 5 length units. Yes? Is that understandable? So that's it. These two theorems, we want to practice a little bit. So don't get confused, okay? So let me draw that picture from other directions. I want to test you what you say. For example, let us say that I have this triangle, and then I would write it as, so here I will draw a line parallel to this one. So let us say that this line is parallel to that. Okay, so now if I write this x, and from here to here a, and from here to here y, from here to here b, what can I write again? I want you to understand this is not necessarily top triangle. As soon as you see one line parallel to the other line, you can write what if you want? X over a is equal to y over b, end of the story. So if you decide to write this part to this part equals to this part to that part, that is end. You cannot continue further. So you cannot bring the length of this one and this one into the game. If you insist to do that, so let me call this Z and C, this is finished here. But if you want to write a relation in which Z and C are also involved, then what can you write? If you write this, you cannot continue with Z and C. You have to stop here. This is correct on its own, finished. But in some questions, they might ask you to know about the length of Z or C. So of course, this is not useful, because this is useful when you want to know something about these four parts. If you want to know something about this one and that one, this is not useful because you see Z and C does not appear. So this will not be able to give you any relation between Z and C. So if you want to know something like that, then you have to decide not to go part by part. You have to go part by the whole. Yes, so you need to write x over the whole part. The whole part is not a, is x plus a. And then do the same thing here, y over y plus b. Then you are allowed to write z over c. Yes? So that is my advice. First of all, you need to see what problem needs from you. If the problem doesn't need anything about the length of these two sides, use this simpler version. But if your problem needs something about these two, this simple version is not suitable to answer. It's better to write that one. Is that understandable? Okay, this is the problem in the book, so let us ask you your opinion. So I will draw it exactly. So a picture like this is given. So it's A, B, C, and they have written a centimeter here. Every length is written in centimeters. And then you have 11, 9, and then you have a parallel line here. Okay, so these two lines are parallel, and this is also MN. And they have given you these numbers. 11 is this one, 9 is that one, 5 and Y, X, and 12. Okay, so my picture is a little bit bad. Let me make it a little bit better if I can. Yes, so here, yes, that's it. These two are parallel. So according to this picture, you are supposed to find the exact values of X and Y. Yes? It's very simple. So if you want to find X and Y, you know that for finding Y, the transversal theorem is enough. But the simple version is not suitable to find X, because X is the length of this side. Whenever you want to find that, you need to use the complicated version, a little bit complicated version, yes? But you can do both. For example, if they don't want you to know about X, which one is better to use here? The simple version, yes? Because if the X is not involved in the problem, and you just need to find Y, so what do? So you write MN is parallel to BC based on transversal theorem. What can I say then? I can write 11 over 5 is equal to 9 over Y. That's enough. If the goal is just to find Y. Yes? How can I solve that? So you know that 11 times Y is equal to 5 times 9, 45, and then Y becomes 45 over 11. Length units. Okay, here is centimeters, so you have to write centimeters. And put the exact values, unless I ask you to approximate it. Understandable? Okay. But if I want to find X, the transversal theorem is not enough. Because transversal theorem doesn't tell me anything about this length and that length. So if I want to use that, I have to use top triangle theorem. Okay, so can you tell me what to do? If I want to use top triangle theorem, then I shouldn't write 11 over 5. So I would say MN is parallel to BC by top triangle theorem. What can I write? I can write 11, but over
16.
Over the whole length, not 5, over 16. Then I am allowed to write X over 12. If I want to, I can use only this theorem to find both X and both Y. Okay? So if you want to write, if you want to continue, what do? You write 9 over 9 plus Y. So here, top triangle theorem was enough, because you can use this part of it to find x. You can use this part of it to find y. That's up to you. If you write this for the previous case, that's also correct. That's up to you, want you. But here, because I already found y, I don't make trouble for myself to do this harder calculation with this fraction number again here. So why should I? So here I would say this is not necessary, since y is already found. Yes? So what I do, I just use this piece of information. So, and then I know that 11 times 12 should be 16 times x. And I am looking for x, so I have to isolate x by dividing by 16. Yes? And then, of course, I see that this can be simplified by 4. This can also be simplified by 4. It becomes a little bit simpler. So it is 33 over 4 centimeters. That's it. So this is what you need to know to solve problems. Is that understandable? So if I want to summarize, you have two theorems, which is related to the case that you have a parallel line to a side of a triangle. It doesn't matter if it is on this direction or in that direction or in that direction. You can write two things. You can write, you use transversal theorem, but in transversal theorem, you have to write this over that equals to this over that, and you cannot continue something for this one and that one. That's end of the story. But if you want to write something about this one and that one, then you have to use top triangle theorem, okay? And then this means that this length to the whole length is equal to this length to the whole length is equal to that one to that. Yes? That's it. Okay, so let me see, before going to the last more interesting theorem, let us try to solve some of the problems here. Okay, so let me show you the book. Yes? May you speak louder? Not necessary, since y is already found, because I found y here, yes? If you want, you can just ignore this in the exam. You only write this, take these two parts and solve the problem like this to find x, and then use these two parts to find y. That's also work. Okay? Okay, so now let me see, everything is working fine. Yes. So here, I don't know which one, these are very simple ones. Okay, so let me just wait for you so that you can solve this very simple problem first. Yeah, just do both parts quickly, so then we can continue. Okay, so I think the problem is simple, isn't it? So which one do you prefer here? You can write 4 over 5, but then you are not allowed to write x over 15. Because the unknown is on mn, the transversal is not useful. Yes, because the transversal theorem doesn't say anything about this length and that length. So top triangle theorem is better. So but if you want to write top triangle theorem, then you should write 4 over. So you need to mention that mn is parallel to BC, so I can use the top triangle theorem to write 4 over what number? 9. 4 over the whole one. Yes? Is equal, then I am allowed to write x over 15. So this is what you need to write. And then 9 times x is 60, because 4 times 15 is 60. And then x is 60 over 9. I simplify it by 3, 20 over 3, and you don't need even the calculator, just write like that. So 20 over 3, if you want, of course, you can put it is 6 point something, approximately. But that's the exact value. Any questions here? So in the exam, you say that MN is parallel to BC. So by top triangle theorem, I can write this. And then the continuation is finished. Here, MN is parallel to that one. Then you have to decide which one you want to do. Again, you see that X is here. Your unknown is here. So the transversal is not that useful for finding X. So I have to use again top triangle theorem. But top triangle theorem tells you that this length over the whole thing, yes? The whole thing is given to be 13. You want to find that one. So what should I write? 6. Because this is given to be 13. This is given to be 7. It is easy to understand that this is 13 minus 7, which is 6. Then I write 6 over the whole number is equal to, what should I write?
3 over x.
3 over x. And then I multiply 6x. 3 times 13 is 39. Then I find x by dividing by 6. So 39 divided by 6. And then what happens? I simplify by 3. It becomes 13 over 2, which is in that case exactly 6,5 centimeters. Okay, so I hope that you learned this. Of course, I will solve harder problems, but I want to go to the next theorem, which is the more interesting one, bisector theorem. Any questions regarding these so far? Okay, so let us now go to the next theorem. So the angle bisector theorem in a triangle is this. If you have a triangle, ABC, and you draw an angle bisector. So it means, for example, there are 3 angles here in a triangle. So it means there are 3 angle bisectors. What was an angle bisector? Is a line that divides the angle into 2 equal pieces. Yes? So, for example, let me choose this one, and I want to draw a line that divides my angle into 2 equal pieces. So I continue here until I hit the opposite side. This line segment that I construct in that way is called the angle bisector. Let me call this point D, the angle bisector of angle A. So here, if I call this alpha, this is also alpha. That is the meaning of being an angle bisector. So there is a nice theorem here. So there is an angle, this nice theorem tells you that if this length is, let us say x, this length, and if this length is y, and the length of the opposite side here is b, this is the common thing in a triangle. If this is capital B, the length of the opposite side is denoted by little b. And if this is capital C, the length opposite to it is denoted by little c. There is a very nice relation between these 4 numbers. Yes? So there is a very nice relation between these 4 numbers. And the relation is this. The relation between x to y is equal to the relation between c to b. It is not trivial. Okay? So, is that understandable? Okay, so that is what the theorem claims. You want to know why this is true. Yes.
Is it the same the other way around?
Yeah. Of course, because there are 3 angle bisectors. You can talk it similar thing for the other 2. But let us concentrate on one of them and understand that. So be careful. You draw one of the angle bisectors, for example, this red line. It goes and divides the opposite side into 2 pieces. Not, of course, necessarily equal, as you see, they are not equal. But something, it is very interesting. The ratio of this over that is exactly equal to the length of this side to the length of that side, which is not trivial at all. Okay? So we want to prove this. We want to understand why this is indeed the case. Okay. So what we do, there are different proofs for this theorem. So let me follow the one given in the book. Okay, I will start it, but I want to ask you what is your opinion about. So the book tells you that you start continuing this red line. So you can continue it forever. And then what you do, so they haven't explained in that way. So let us take my compass, okay, put the needle of the compass here and open it to the size of this. And then in my head, I will do something like that using that compass. We don't have the compass here, but you understand what I mean, you know. I take this is, imagine this, my hand is from here to here, and then I take it and then find a line here. So for example, it would be somewhere here. Yes, and then I connect it to this. So what I did, I just continued this. Might be this is not a good picture. You should imagine what is happening, you know, because my picture is far from being precise. We can use GeoGebra to understand it better if you want to, but try to imagine what's happening. So what I'm doing, I continue this one. So it means I put my ruler here and I continue it, and I can continue this forever. Then I take the compass and put the needle of the compass here and open it to this size, and then bring it down here and then find this one. Of course, it should be a little bit lower. Yes, do you agree? And then whenever you found that, you connect these 2 points. If you understood my construction, if I ask you what you expect about the length of this green line, what do you say? What? C. Do you agree? So you understand? Yes? Exactly. That is C. Yes? Understandable? Okay. But if I ask you now about the size of this angle, can you say something about the size of that angle that is constructed here? Not A. Alpha. Yes? Why is this alpha? Because now this bigger triangle is what type of triangle? You see, one side is C. This side is also C. So this triangle, the narrow triangle, is constructed in this way here, is an isosceles triangle. If it is an isosceles triangle, whatever the size of this angle is, the size of that angle should be the same. So if the size of this angle is alpha, the size of this angle is also alpha. Understandable or not? Okay. But now concentrate on this triangle only. Tell me why this triangle is similar to this triangle. Why they are similar? No, this is a smaller triangle. Yes. And this one. Yes? Alpha, alpha. No, this one. As this one. Yes? Because these are vertical angles. So this triangle and that triangle are similar because they have 2 angles of the same sizes. Yes or no? Yes. Okay, if these 2 triangles, if you don't mind, do you remember the name of it was D? I don't know, for some reason I erased that. So can you write for me the relation? This is a good practice from Math 1C. So I know that these 2 triangles are similar. If the triangles are similar, I know that I can write 3 relations in general. I'm just practicing. One of them will not be necessary. I just clean it later. But let us practice. If you want to write the correct ratio, you need to decide about the sides of one triangle. So let us concentrate here. One side is AC. One side is CD. One side is AD. Yes? I decided to write the bigger ones on top. I could do the other way around. Okay, but now if I write AC, which one of these sides I have to write below AC? Yes?
I don't see a D.
D here.
Yes.
Yes? If you don't talk, you will see. Okay, but you're continuously talking. Anyway, you can work in BBC, yes? Because you're reporting, broadcasting news everywhere. Yes. Okay, so here, anyway, tell me, if I write AC from the bigger one, can you tell me which one of these three I should write below AC? It's just a practice from Math 1C. So let me write E here, so to be consistent. BE, do you agree? Because AC is opposite to this angle is equal to that angle, and the opposite side is BE. So you are right. If I write AC there, I have to write BE here. Okay, tell me, if I write CD here, what should I write below it from these three? Which one? BD. Why? Because CD is opposite to alpha. Opposite to alpha here is BD. So I would write BD. AD, if I write AD, it is clear what should I write. There is one left. If I write AD, DE is left. But this is not necessary. So you don't even need to write it down. I just wanted to practice. Okay, so now what is another name for AC? Look, AC is B. What is BE? BE is C. What is CD? CD is Y. What is BD? BD is X. So I was able to prove this. Of course, if B over C is equal to Y over X, then C over B is equal to what? You tell me. X over Y. So it doesn't matter. That is exactly what we wanted to show. So you see, this is a little bit hard theorem. The person who proved this theorem, who found this relation for the first time, he was smart enough to construct another triangle to convince himself or herself about this relation. Okay, but anyway, this is the reason why this theorem is correct, but we mainly want to learn how to use it. It is, of course, for the people who like mathematics, it is useless to just memorize things without knowing why. So that is the why behind this relation. Every theorem has some kind of component. So here you have to have a triangle, you have to have an angle bisector, then you can write this. Okay, so let me practice with you how to write this theorem in different directions. I want you to understand that as well, because that is a skill you need to learn. And it is easy, by the way. So let me draw 3 pictures for you and try to come to them one by one. So one picture, let me repeat the same picture here, more or less. Okay, so here A, B, C, I call it C, I call this B, and I draw this angle bisector, and then let me call this little part X, this little part Y. Now I try to copy and paste more or less the same triangle. Of course, I will not be able to do that by hand, but you can imagine I did. And this time I want to draw this angle bisector. I call this D. Okay, and then here I show it with little a, I show this one by little c, I show this one X and this one Y. And then finally, I can imagine a similar picture in which the other angle bisector is drawn, yes? This time I try to draw this angle bisector, divide it into 2 equal pieces. Okay, don't think that because they are equal, these sizes should also be equal. No, unless the triangle is an isosceles triangle or an equilateral triangle. Okay, so let me call this D. This time I call this X, this Y, and this one B, and this one A. Okay? So we should be able to write that theorem in all directions. This is exactly what we did. But how should I understand that? These pieces separated by the angle bisector, you write in one way that you like. For example, you choose X and then you choose Y. You could choose the other way around, it doesn't matter. But when you choose, you have to respect your choice. What do I mean by that? So you need to imagine X is close to which side? Is close to side C. So if you decided to write X above, then you have to write C above. And then this one is close to this. So if you have chosen to write y here, you choose b here. This is the way that you write it. If the angles are the same, so let me put a dot here and a dot here. They are the same. Is that right? If these two angles are the same, what can I write now? Can you tell me? So this angle bisector gives you two lines, yes? Separates two line pieces here. So you write one of them on top and the other one in the bottom. And then if you decide to write x above, which one of these you need to write above here? C, because x is close to C. And then which one you need to write here? A. This is for this picture. And if these two are the same, again, you write x over y equals to what? B over A. So that is the content of the angle bisector theorem, and it is extremely simple. Okay? Any questions so far? Okay, now let us do some problems in the book. Okay, so again, let me start with an extremely simple one. I want to wait for you, this is very simple. Yes. You want to solve this problem. I want you to find exact, so you don't need your calculator. Okay, so this is extremely simple, Des. So you understand that because they are putting a dash here and a dash there, they are telling you that these two angles are the same. So if the angles are the same, it means that that line CD is an angle bisector. So this means that you can use this theorem safely. But you need to know how to write it down. So what should I write?
8 over 6.
If you decide to write 8 over 6, that's okay. But then you have to write which one over which one? 16 over x. That's correct. Or you could choose to write the other way around. So anyway, 8 times x is equal to 6 times 16.
96.
You don't need to multiply because 6 divided by 8, it becomes simple, yes? Because 8 and 16 are simplified 2 times. 2 times 16 is 12. That's the exact value. Yes? Okay, so that was also very simple. So that was the content of what we learned. Okay? Now I want to wait for you so that you can do this problem. Now that you learn, so you can use them whenever it is necessary. Yes? So I want you to work on this problem. Yes? In the following figure, so we know that these three lines are parallel, and some numbers are given to you, and some values are missing. So you want to find the value of x and y, precisely. I want to wait for you. Okay, so let us do it together since there's no time now. Okay, can you help me to do it? I don't know, you have to decide which one you want to do first. For example, if you want to do x first, the transversal theorem is not useful even though it looks like that. Why? Because then you need to write this one over that one. So far so good. But then you have to write this one over that one. None of them is given to you. So even though it seems to be a transversal theorem, it is useless because I do not have any pieces of information regarding these sides. So this motivates me to do the top triangle theorem, but there is no top triangle. That's always left triangle here. So you can momentarily in your head forget about this. Don't distract yourself. Just concentrate on this one. So then you write what? You write 6, but over? No. If you write 6 over x, it's not wrong. You have to write AD over DF. It's not wrong, but neither A. So how many unknowns you have? 1, 2, 3. So it is useless. It is not wrong, but not useful. Yes? So you write 6 over now?
6 plus 6.
The whole thing. 6 plus x. Then you can write what? Then you can write what? 4 over 7. That's the only thing you have to be careful of. And then This is equation. How many unknowns you have? 1. So it is solvable. So I would say 4 times 6 plus x is equal 6 times 7. I multiply 4 in. 24 plus 4x is 42. I move this to the other side. It becomes 18. I divide by 4. So it becomes 4 comma 5. I think if the, of course, if the units are centimeters. Otherwise, you just write length units. It is not mentioned centimeters, so let us be careful. So you just need to write length unit. Length units. Understandable? Okay, now you need to find y. For y, you have two alternatives. You can ignore this line, consider this one and the bigger one. You can consider this one and the bigger one. That's up to you. So which one you prefer? I would prefer the smaller one and the bigger one. Yes, because I have less unknowns. Yes. So in this case, ignore this in your head. And then what happens? What should I write now? Can you tell me? I should write from here to here 6, but over
15.
the whole length. Yes. 6 plus 5, 11 plus that, which is I already found, 15, comma 5. Yes? And then it becomes equal to what? 4 over 1. And then 6 times y is equal to 4 times that is 62. So y becomes 62 divided by 6 length units. Of course, I can simplify this. It becomes 31 over 3 length units. That's it. So you see the problem is not complicated. Yeah, it was a level 2 problem, but it still was very manageable. Any questions? Understandable? So we will continue with a little bit harder problems tomorrow of this. And there is one topic of this geometry left, and then we will go to statistics a little bit. Next chapter. Any questions? Okay, thank you.